All right, welcome everybody to Harnessing AI for Advanced Network Security, from attacks on privacy to defense innovations. Thanks again to our diamond sponsor, Island, along with our other sponsors for this session, Sumo Logic and Palo Alto, and of course, ISSA for bringing us all here. Dr. Matt Wright is a professor at RIT and the chair of cybersecurity there as well. Also at RIT, Nate Mathews is a PhD candidate and focuses on the intersection of privacy, security, and deep learning. So hopefully we'll have a good show. I'm really looking forward to this one. Thank you, gentlemen. Round of applause, please.
You can always tell it's going to be a good audience when they clap before you even say anything, so that's good. So I'm Matt Wright.
I'm Nate Mathews.
And we're going to talk about how to use AI specifically for network security. And we have a coffee theme that you'll see throughout the talk. All right, so I wanted to start with a little story. Some of you may have heard it, but it's been 5 years, so I'll remind you of what happened. NASA got hacked into, and the headline, as you can see, is because of an unauthorized Raspberry Pi on the network. So to give you just a little bit of what happened, I'm not going to give you all the details. So we have this attacker, and the attacker is going to connect to the NASA network, and they find this unauthorized Raspberry Pi, right? So they use that as a starting point for launching their attack. And then they're going to pivot. They're going to compromise a shared gateway. And from the shared gateway, having compromised that, that means they can get into other subnets. So they connect to a different network. And within this network, they can connect to a target server and compromise that. And from there, they were able to extract some 500 megabytes of data on Mars missions. Some of it apparently was quite sensitive. And the key to, a key part of their attack process, as we see in a lot of attacks, is that they were doing pivoting. They were connecting to different machines, and in fact, what I didn't show you is that, of course, they wouldn't have just directly connected from their computer to the NASA computers. They connected through some other chain of computers, finally with some kind of compromised other personal host before getting to the NASA computer, right? It's a very familiar story for those of us in cybersecurity. Now, since you are all, or not all of you, but a lot of you are practitioners, I am actually quite curious to know what kinds of indicators of compromise or other things or things that you would do to try to prevent this attack. So either prevent or detect this attack. Nobody in here does any security. Okay. Right. So the natural thing, and of course what hit the headline, is you should scan your network periodically for unauthorized devices, unexpected devices, right? And then you should have an inventory of what else is on your network. And for sure, that's a clear starting point. What else could they do? Yes?
Probably started with a scan, although that's noisy. There's probably some kind of scan to find that target.
Yep, you could look for a scan. That's one indicator of early stage compromise. Yeah? Absolutely. You could do some kind of anomaly detection. You can patch your vulnerable systems so that your gateway is not compromised, your server doesn't get compromised. What else? Yes? Use a NAT, right? Yep, try to make sure that people can't be connecting to all your just internal devices. You can encrypt the data. Now that, of course, is a trade-off, as you all know, because if that's data that you're actively using, then you have to have good systems that enable people to be able to use it and access it without just leaving the keys all over the place, which negates the point of encryption. So challenging tasks for sure. There was one other over there. Locking down the MAC address. Okay. Okay. So what we're going to talk about today is to focus specifically on the pivoting itself and say that this is a mostly in practice, largely untapped opportunity to potentially detect attackers. And I'll just have to highlight for those of you who are in practice, this is a research project, so we're not doing something that is going to be in a product anytime soon. But it is an idea that's been around for a long time, and a lot of this project is focusing on making it more practical. And that idea is to do something about, well, can we detect the pivoting itself? Because when the attacker, well, let's switch to the next slide.
Yeah, so real quickly,
Oh, yeah.
How many of you have potentially identified or seen pivoting in practice? A couple, that's great.
A couple more over there. So.
Okay. It's good to see that it is a real problem that you're encountering. And in particular, as of recent, there's been some studies and just I think in the last couple months, I think it's Rapid7 did a review of I think 100 so like compromise campaigns and critical vulnerabilities, and amongst that set of surveyed events, what they identified was rather interesting. In that something like 60 to 70% of the identified 0 days were specifically in regards to pivoting, and specifically pivoting on edge devices. And the reason I wanted to bring this up is specifically because, well, the previous scenario that we just looked at was a unauthorized connected Raspberry Pi to a network. That's something that you can more easily identify as it's an unknown device that you could pick out and block without needing to do our fancy stuff. But for a lot of environments, you're going to have a lot of IoT or other devices along the edge. These might be things you can have direct control over, or they might be proprietary tech that you're not going to have the internals of. In these scenarios, it's going to be very helpful to be able to identify these events from a network perspective rather than a like host or device identification spot. And that's where our method comes in.
Okay, so we are going to talk about the detection of pivoting itself. So can we determine that pivoting is going on? So we're going to start out with a couple of basic concepts of pivoting that will be helpful throughout the duration of the talk. Then we're going to talk specifically about how do we, and we're going to be using machine learning in our approaches, so how do we take traffic information and turn it into data? Then we're going to talk specifically about some of the deep learning concepts that we used in our work, and end with some of the experiments that we use to demonstrate the effectiveness of this approach. So some of the concepts of pivoting.
Let's do
this yours?
I think it was mine.
Okay, you go.
Okay. So to do a quick overview, more formally of what a pivoting attack looks like. Let's say you have your network environment. You've got a number of different machines on that environment. On that environment, you might have some machines that have more sensitive data than others, and these you're probably going to want to protect more. And hopefully in your environment, you have some amount of security sectioning done to segment off these really sensitive locations. And you might have hopefully several with different levels of security.
Unless your zero trust is so good that you really, really don't do any segmenting, that's interesting. I'd love to hear from you after the talk. But
so an attacker will probably need to get access to your network. They're going to be targeting edge devices first. And if they can find one that's got a juicy vulnerability, they can get access that way. But this is only going to get them so far, and from this kind of low privileged location, they're going to need to move, I think, laterally along your network to eventually build a connection vulnerabilities and a tunnel up to your sensitive data store. And this is what we call a pivoting chain or a stepping stone chain, with the various hosts between the attacker and your sensitive target is what we call stepping stones. Let's see. And so a potential way to go about trying to identify when this event is occurring is to try to look at, along your network, instances where the same traffic is reoccurring in multiple locations. Because that's going to give a strong indication that something odd has gone on in your network. And so you can do this, your task is ultimately to compare your PCAP or network traffic data to identify when a pivoting chain has occurred in your network and separate this out from your benign PCAPs or like miscellaneous traffic in your network.
Okay, so there's different models that we can use to think about how we might want to do this pivoting detection. In the first model, and so this is the same, very similar to the diagram we just saw. Next, you've got the clicker, so, oh, sure. All right, so in the model that we just saw, we had the target with the gold bars, okay? So same idea, we've got the target, we're gonna have two stepping stones. One way you could do stepping stone detection is on the host. So you could have the host gathering its local network information in order to see that I have a connection here S1, and it looks a lot like the connection here S2, and that's what's going to lead me to believe that I have a potential stepping stone or pivoting attack happening on this host. The next thing that you could look at is over the network. So this could be in a network intrusion detection system with different sensors at different locations. And if here you see that there's a connection between this point and this point, then maybe that's the signal that you're using to say that this is a stepping stone. And then finally, we could have watermarking. Now, this is a more advanced technique where you're actually going to be modifying some aspect of the traffic. Usually, it's just the timing of packets. You might add small delays to some of the packets in a pattern and then look for the pattern to show up elsewhere. So in this case, if this yellow node is doing the watermarking, then those watermarks will appear at, of course, that location as well as E2 and E3. And so that's a third way. We're not going to talk much about watermarking in this talk, but that's another way you could do stepping stone or pivoting attack detection. Another concept that we want to make sure that everyone has a good idea about is the base rate fallacy. How many of you already know about the base rate fallacy? Okay, it's a pretty common concept if you study intrusion detection systems because a very similar thing happens, and I think you'll get a sense of that as we go. So what we have here is a victim network, and we're worried, let's say we're doing host-based intrusion detection, and we're worried about somebody here attacking one of our internal hosts using this as the stepping stone. And we've got, let's say, n external connections to this host, and then m internal connections to hosts over here. And if we look at every possibility of a stepping stone, we have n times m pairs, right? It could be any of the incoming connections, could be paired with any of the outgoing connections, and we kind of need to look at all of those pairs in order to figure out, are there any stepping stones here? And if you have, let's say, just 100 external, 100 internal, to keep this simple, then And let's suppose that you have a stepping stone detector that it's, on paper, really good. 100% true positive rate. That means every stepping stone that goes through, every time an attacker actually does a pivoting attack using this node, you will detect it guaranteed. That's not something anybody can really offer in practice, but let's pretend that that's available. And let's suppose that there's what you might consider to be a low false positive rate. Any machine learning person in almost any application space would be thrilled to have 100% true positive rate and only 1% false positive rate. In almost any application space, that's quite good. If you go to the doctor and you take a medical test for something and there's only a 1% false positive rate and there's no true negative, or there's no false negatives, you are going to be pretty convinced by the output of that test, right? Now, that said, in this situation, how many of you think that this is going to be a very good stepping stone intrusion detector? A couple brave hands. I should have phrased it the other way. How many of you think this is going to be a really bad stepping stone intrusion detector? Okay, a few hands. I don't know, is that 50-50? If 5 hands say one thing and 3 hands say the other out of a crowd of 50? I have no idea. So it turns out that the answer is no. And the reason for this is what we call the base rate. You're looking at all the possible pairs, and how many possible pairs are there? Well, there's 100 times 100, so there's 10,000 possible pairs. And 10,000's a lot. And so if you look at the false positive rate, that means you're going to have, on average, about 100 false positives and 1 true positive. So now you've got your person going through 101 alerts, and 1 of them is real. You're probably not that excited about this system. So that's one thing to keep in mind. We're going to want to do even better. Even though we say 1% false positive rate, that should be pretty good. In our case, we really want to do better than that, if possible. All right, so we've talked about some basics about pivoting. Let's talk about how we get from some network data to something that we can actually do some machine learning on, which, how do we get some data, and how do we do detection on that data? Anybody know what that might be? There you go. It's a Wireshark screen cap, and we have a whole bunch of information here, and we're not going to use it all to do this. And there's a lot of reasons you wouldn't want to necessarily look at the data. A lot of it is just pure performance reasons. You wouldn't want to have a special thing that's going all the way to do completely deep packet inspection. So we're going to, and of course, a lot of data these days is encrypted. So you're not going to be able to do a lot. Now, if it isn't encrypted, you could definitely see a stepping stone, right? It is not hard. You could look at the content, and they more or less match, and there you go, you're done. So we're going to assume the more complicated, and these days more common situation where there's a lot of encrypted data that you need to worry about. And of course, the attacker is going to be using the encrypted channels, right? So what we're going to focus on instead is the metadata, right? The stuff that you can see in the header. And that's going to be easier to get that at faster rates. And of course, it doesn't rely on needing to break encryption or something like that in order to get access to the information we need. So we have a bunch of packet header information. What are we going to try to extract out of it? Well, we're trying to get some patterns that a machine learning algorithm could actually use and do something better. So as an example to see that, we have data from 3 websites. A couple I think you're familiar with, Google and YouTube. This one in the middle happens to be, we have a South Korean partner, and so she put this in. Naver apparently is the South Korean social media site. So we have these 3 different websites, and we get 3 very different looking traffic patterns of packets that go back and forth. And I think just intuitively looking at it, you would say, well, if I could look at this as a human, I could probably pick out the difference between this thing and this thing, or even if you look carefully enough, this thing and this thing, yeah, those are two pretty different things. So if I could see those pictures, I could pick them out. And if you've been following the news at all, you probably have some idea that machine learning is getting pretty good at picking out patterns. So you might imagine that it could also pick out those patterns. Here's another way. So this is basically based on the sizes of packets, which is a key piece of information that we're going to use. Another key piece of information we can use is the timing of packets. And again, we can see distinct patterns. So even though this thing looks kind of like this thing, now we can see that the timing of the two websites is actually dramatically different if we look at them over time. So we can say pretty clearly that these two sites are different. And again, with machine learning, we're going to be able to pick out those types of patterns. So that's the kind of thing we're looking for in the traffic. So taking a step back, I said, OK, we've got these PCAPs. We're turning them into, we're looking at just the headers. How are we going to turn that into data? Or as in machine learning, we talk about features, which is just like what aspects, what things in the data are you actually concerned about? So first, what we can do is we can look at the packet sizes, right? So we can see that, OK, there's this size of packet going from the client to the server, and then a bigger packet went out, and then some packets got received, right? So we can look at that as the beginning of the pattern. We can also look at the timing. How quickly, when did we go from this packet to this packet? Versus we have this gap between that packet and the next packet. Here we had a few packets real quickly in a row, but then we had another gap, right? So those kinds of patterns are the information that we need. What we need to do this for machine learning is instead of turning it into a bunch of pictures, which are better for you and I to talk about, we're going to turn it into tables of numbers that are easier for the computer to work with. So in particular, you can see that, for example, just we have a packet, and then we have another packet that are both going outgoing, and then we had another packet go the other way, incoming, and so for each incoming packet, we'll subtract one. So we keep a cumulative sum of each of the packets. Or we could we could just assign, say, +1 to each outgoing packet and -1 to each incoming packet. And we keep that as two separate pieces of data. They're both capturing the same thing, but it actually turns out that it's useful to have different ways of looking at the data when we do our algorithms. Just skipping down, we can look at the timestamps. We could also normalize the timestamps and just say, well, what's the packet inter-arrival time so that it goes from the first one to the second one to the difference between the second one and the third one. Or we could add 1, just the value 1, for dumb mathematical reasons we don't need to get into. You can just add 1 to every timestamp value or inter-arrival time, and that turns out to be helpful. So these are the types of things that we're going to be doing to extract information out of these network traces, these PCAPs. Given all of that, we can put them into a machine learning model. We'll talk about the nature of the machine learning models later in the talk, but you can do this with actually pretty standard machine learning models. It works decently well. When I say decently well, at the level of like the model that I said at the beginning in the base rate fallacy example where you have 100 false positives and 1 true positive, but 1% false positive rate. So it sounds pretty good on paper, but again, we're going to want to do better. OK, so the next concept that I want to get into is metric learning. And this is going to also be really helpful for understanding what our actual models are doing. So we have all this data, and we put them into other types of machine learning models. But we're going to be putting them into neural networks. I'm not going to ask you to understand everything that's going on inside of a neural network. But I do want you to know just one thing, which is, OK, so we've got these neurons. This is essentially what a neuron is in a neural network. All it's doing is taking you've got these inputs, you multiply them by weights. So you multiply each value by some multiplier. And so the first one, x0, you multiply it by a weight w0. So you take all the numbers that you had, you'll multiply them by some other numbers, and then you add them up, essentially. You do another small additional mathematical operation. A lot of that can be simply y equals x as long as it's positive. If x is negative, you take 0. And that's the type of very simple function that this is. And then that gives you the output. And now you're going to create a whole network of these, and that creates your neural network. And the only thing I really need you to get out of that is there's a bunch of weights, and the weights are important to the learning. Yes, those are called weights. I just said that.
And then real quick addition there is in that example, there was just 5 weights. In practice, for example, our model uses, I think, 1 to 3 million parameters, weights. And ChatGPT is instead on the orders of billions of parameters. So the number of parameters or weights in a model is like a proxy for the level of complexity that it could potentially track.
And the amount of computation cost to both train and use the model. OK, so we've got a thing, a blob of all these weights, and what do you do with them? And first, you take the data, and you feed it into the neural network, and it gives you answers. And what happens at the beginning is that you initialize all the weights to be random. Well, this is basically like saying you start with your brain completely mixed up in a blender. It's not going to work too well. Right? It's going to give you some really bad answers. But that's OK, because some of the answers will at least be better than others. And each answer that it gives you, you say, well, how good was it or how bad was it? So you have what's called either an objective function or a loss function or a cost. And then, based on the values that you get here, you adjust the weights. And you start moving them around. So with each answer that you get, you're moving some of the weights, changing some of their values. And eventually, you get something more recognizable, right? So you've unscrambled the brain, as it were. And so that's the basic idea of a deep learning model. But for most of the rest of the talk, you can treat this whole thing as a black box. You have to understand that there's some training that goes along in this in order to understand a couple pieces, but we do some training by giving it some data, seeing how wrong it is, telling it how to fix itself, and then it gets a little bit better. And we do that many, many times, and eventually it gets pretty smart. So then I mentioned this concept, metric learning. So now I'm going to explain what that is. And I'm going to compare that to another thing that we do in machine learning a lot, which is classification. Classification is very simple. It might be like, hey, here's a piece of software. Is it malware? Yes or no? And we work on models that do that as well. But here's another example that is easier to put up on a slide. We're going to do the identification of some fruit. So we have an apple, we have an orange, we have some bananas. We have a new piece of fruit. And we go to the neural network and we say, hey, what piece of fruit is this? And it's going to take the information that it has about the new piece of fruit, and it's going to use the weights that are in its little brain, and it's going to say, well, I think it's very likely that this thing is an apple. It's a lot less likely that it's an orange, and much, much less likely that it's a banana. Okay, so that's what I think that this is probably an apple. Okay, so this is classification. But we can do something a little bit different. We can say, all right, so model, instead of giving us the answer at the end, I want you to give us a vector of numbers, which is the thing that you would use just the last little step before you actually figured out the final answer. I just want the numbers. I don't want the actual answer. So the step before you even give us these numbers, the 90%, there's another step that's inside kind of like on the edge of the brainstem, you could imagine. Right? It's just sitting there, and it's about to say, but I could tell you that it's an apple 90%. No, I don't want that. What I want to do instead is to say, well, I have feature vectors for some bananas, and I have feature vectors for some oranges, and I have some feature vectors for some other apples. And what I'm going to do instead is I'm going to take the feature vector that you gave me, and I'm just going to compare against these other feature vectors. And now I'm just going to pick the one that's closest. And this is called metric learning. Now, I'll give you one example of why we might do this instead of the first thing. One reason we might do metric learning is, what if we get something that's not a fruit? It's round, it's got some color, it could be a fruit. The computer doesn't know until you've actually put it into the trained model. If you put it into this trained model, it's going to, I don't know, probably guess orange or apple, right? It's going to guess one of the round fruits because that's what it's been trained on, but it doesn't know what else it could be. But what we can do with metric learning is say, well, this thing is, yeah, it's not actually that close to any of these. Yeah, it might be closer to orange than it is to banana, but it's not really that close to any of these things. So maybe we shouldn't treat it as one of the same fruit. Maybe we should say that it's a non-fruit, and then move along. And that, of course, would be a better answer than trying to guess that it's an orange. And so to take this, by the way, back to the original idea of our stepping stone detection, our pivoting detection, if we have a network connection and we are looking at it and we're saying, oh, I've got this network connection, which of these outgoing ones does it match? Most of the time the answer is none of them, right? And it shouldn't be trying to just find the best match. It should also tell us, is it any of these or none of these? All right, so a little bit more about these feature vector things that I showed on the last slide, because I just said, it's a feature vector. So when we do machine learning, a lot of times what we will want to do is represent stuff as a set of numbers, a vector of numbers. And for example, this could be a representation that we use for king. And we might think of the different numbers here as, now this is not actually what goes on in the computer in terms of this stuff on the left, the labels, but we could say, okay, the royalty vector, royalty value in the vector, that's really high for king. If you see king, royalty, those should go together. Masculinity, well, king is the masculine form of the royalty, so that should be very high. Femininity, that should probably be low. Age, that should probably be relatively high, like compared to prince, for example. And we can do the same thing for other words. Queen, woman, princess. We can assign, so you can see the queen should also be really high on royalty, not very high on masculinity, but instead really high on femininity, right? So you can kind of guess how all of these might go. And another thing that we can do with it is, suppose that we've got king, and suppose that we've got the vector for man. And now if we take the vector for king and we subtract the vector for man, we get the vector for royalty, right? Non-gendered royalty. And if we add in the vector for woman, we get something that's awfully close to the vector for queen. Right? High on royalty, low on masculinity, high on femininity. And it's really helpful to be thinking of all of the data that we have in this vector way, because we can then do things like, when I say a vector, a feature vector is close to another feature vector, king is closer to man than it is to woman. King is closer to queen than it would be to say princess, right? Man and woman have the same distance in this broad direction, and it's not as far as this distance. There's some other aspect, some other element to the vector that's pushing it in a different direction. Is there anything else to?
No, I think the only thing to add here is in like the language space, you can have really clear features in these feature vectors. In practice, when we feed our network traffic into it and feed it through the black box AI model, we have no idea what these features mean. They're very uninterpretable, but they're still very effective potentially, assuming that the neural network learned good stuff.
Okay, so metric learning is going to be really helpful here because, so I mentioned before, it'll help you separate the balls from the fruit, right? If you have things that are not connected to each other, we can say, oh, they're not connected to each other. When we do this metric learning, the way we train the model is that we give it this anchor. So we say, okay, I've got some traffic. I have created the traffic myself, so I know that it has a pivoting attack inside of it. I see the pivot go through input here, output here. I know which one is connected. That's the training data. I know these are connected because I made it myself and I labeled it. So I take one end of it and say that's the anchor. I take the other end of it and say that's positive. That is to say, those two things should be well aligned to each other. They should have very similar traffic patterns. And then I take some other outgoing traffic pattern and say, well, that's negative. That isn't connected to the anchor in any way. And I know that, again, because I made the data, so I got to see it and I labeled it. And given that, I can get the feature vectors for all three of these, and I can start comparing them. And when I first start out, again, that neural network is a random scrambled brain and doesn't know anything. And what can happen very frequently is that the anchor is in that metric, those metric vectors, it's going to be further away from the positive and closer to the negative, right? Which is wrong. That's not what we want. With training, what will happen is that it learns to create those feature representations, those feature vectors, in such a way that the anchor and the positive get close, the anchor and the negative get far away. And that's going to be awesome because then when we test on real examples, we only will see two things that are close to each other in cases when they're actually an input and an output for a pivoting attack. Any questions at this point? I know we've gone through a lot of complicated material over here. Yeah.
Where point in the network are you collecting the data from another matter? I mean, are you collecting it from where your IDS would be? Are you collecting it from the pivot point? And I'm done.
Yep. So the question is, where do we collect the data? And we have done some experiments both where we collect the data at the pivot point at the host, as well as we don't actually collect on a network device per se, but instead we'll collect at one host and then collect at a different host if we're assuming that it's going across multiple points. Yes?
Are there other methodologies to train the model, or is this the standard methodology?
This is one method. So the question is, are there other methodologies to train the model? There's many methods to train models. The one we're showing you is the one we happen to be using. And we think it's good because it's worked for us, which we'll show as we get towards the end of the talk. But the answer is, yeah, there's many different approaches.
How do you measure the vendors doing a model? How do I know it's any good? Is there some standard way to detect maturity in their model or best practices?
What I would say to that is that every vendor is going to get to the bottom line relatively quickly, which is just what's the accuracy. And what's harder to understand is actually, to that gentleman's point, well, how did you train this thing? Like, where did you get the data? How did you set up the points to figure out where these things are. And if they can't answer some of those important questions, then you have a problem. Any other questions? Yes.
You're looking at this timing and size.
We're looking at timing and packet size as, and which direction is it going in or is it going out as the kind of the three most important pieces of information for us.
Okay, so like if the network was set up to re-encrypt at every point,
That's right. So we
that would not
assume.
matter to you.
That's right. So yeah, we assume the attacker is using, like, for example, one SSH session to go from point A to point B, right? And then using that and tunneling through that, another SSH session to go to a third point. And they could be using any different SSH is a good example for us. But
Yeah, like they could use any type of covert channel, for example, that we could match to back to SSH if need be. That's the power of the deep learning model in network.
I'll take one more and then we'll go on. Yep. Oh, sorry. We'll take two more then. We have one in the back first. Oh, I forgot the mic thing.
Where are we going?
The question I had was regarding the volume for the PCAP. So if it's coming in this regard, are we talking about a lighter load? Are we talking about a larger load? From my experience, the Wireshark seems to be better for the smaller loads versus like a T-Shark for a larger data set.
So Wireshark is more just for an example. I think when we process our data, we use T-Shark, but I've not done any particular benchmark. Ideally, you'd want to use the quickest method or tool to extract all the metadata, because that's all you really need is the very basic direction, size, and time.
And one more.
Very quick question. So you're using packet header data.
Yep.
So why not just use summarized packet header data from an intermediary device via NetFlow instead of doing it on the host itself?
Yeah, that would work entirely. As long as you've got the per packet metadata points, then that would be perfect.
Right. Yeah, some NetFlow data provides that level of detail, and some NetFlow data does not. It's more aggregated. We need more fine grain. Okay, so why might we do this? Sorry, we're going to move on towards to make sure we finish close to on time. One reason that we would do this metric learning, in addition to the reason I said before, is that this part here is relatively expensive. Taking the data and putting it through the neural network, that's a relatively expensive operation. Like tokens and GPT, right? You can think that, okay, that means you need probably specialized hardware and you need to run it a certain amount of time. So we don't want to do that, especially in training, any more than we have to. But what turns out is really, really cheap is this. These comparisons between the anchor and the positive, between the anchor and the negative. These are very cheap comparisons to make. So this is going to be really saving us a lot, particularly if you remember this figure, right? We have just 100 incoming connections, 100 outgoing connections, but that's 10,000 pairs. And 10,000 pairs is, if we were doing the neural network across the pairs, it would be 10,000 computations. But instead, we're doing it 100 times, once for each external connection, and 100 times, once for each internal connection. So only 200 times that we need to do this. And even if, as we'll see in a minute, we do a little bit of extra computation on top, it's still going to be significantly cheaper than doing the 10,000 pairs.
So we're probably going to need to burn through these slides pretty quickly. So the high level, probably the next set of slides is, in addition to the method we showed so far, there are lots of other little, let's say, tricks that we can apply to try to improve performance further. First idea is amplification. So we take the idea of, rather than, so think, let's say you're flipping a coin, and if the coin is heads, then you win, and if it's tails, you lose. A single time, you're going to have a 50-50 shot at winning. If we adjust the problem such that you can now flip the coin n number of times instead of just one, then the additional number of times that you do, the more likely you are to succeed ultimately, if all you need is one of those coin flips to end up heads. We can apply the same idea to network traces by, instead of doing a full network trace that we encode into a feature set and do comparisons, we can chunk it up into bits and feed each window to produce features that are window specific and then compare windows. And when you can see the scheme that we do this in, you can then vote on the windows to identify if the overall flow is correlated. And we first evaluate this on Tor flows in a privacy de-anonymization setting. And in this setting, it does significantly better than prior methods. So bottom is the error rate, top is the detection rate. Bottom is also log scale, so each factor here is a matter of 10 times improvement. You can see between ours is blue at this edge, comparing at 10 to the negative 4 false positive rate, we are it's above 80% improvement of detection. And at this scale, it's actually potentially useful, where the prior methods had far too much error that you'd have too many alerts getting flagged. Now we can improve on this further. While I'm sure everybody is aware of ChatGPT and the large language models, you might not be familiar with why the LLMs have exploded in the past couple years. In addition to data availability, there's also this new architecture called transformers, which is pretty nifty and is significantly more effective than prior methods. We don't really have time to dive too much deep into it. The basic idea is old methods are convolutions. Key problem with them is while they were effective for old tasks, they only look at local spatial patterns. New method uses what's known as self-attention, which is going to compare to itself in a lot of different locations. And you can do that for every point in space. It's going to compare to every other point in space, which lets you capture global relationships.
Well, let's actually do this one give it enough time so that, yeah. Anybody know what this is? Any idea? Oh, very good. Okay, I hear some cat noses. Okay, so put it into context. So this is where it appears in this image, right? If you thought it was like an alien squirrel, you wouldn't be faulted. But now that you can see the size of it, and now there's the full image. Now, yes, it is a cat nose, but it really helps to have the rest of the information, not just the nose, in order to pick it out. If you're an expert on feline noses, then maybe you could have guessed that was a tiger nose, or if you had known that RIT is tigers. But otherwise, you probably would have guessed just house cat, for example, and it would have been more difficult without that global context. So that's what transformers can really do well.
Yep. And we could probably show off real quickly some results. So here's our transformer version compared to our older method, Deep Coffee, which only looked at local spatial patterns. As you see, another big improvement. So we had a big improvement before, and now we even have a larger improvement. This is still in Tor setting.
So that false positive rate at the bottom, 10 to the negative 6, right? 1 in a million. Instead of 1 in 100, 1 in a million. So that's much, 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 much better, right?
Yeah. Now the number of alerts that you're going to throw that are bad are going to be probably negligible, at least in Tor setting. So we adapt this to stepping stone intrusion detection or pivoting. To do that, we had a lot of issues with actually getting real samples and finding existing open source data sets that we could pull samples from. And we need a lot of data to train a deep learning network. So we built a little kind of synthetic environment with Docker containers, with various different tunnels. And we use this to collect a couple different data sets with the mixtures of the protocols being applied for the pivoting chains. And now, so we test on only SSH only. We get really good performance, above 90% detection at really, really low FPR, so that's great. When you have covert channels in the mix, that hurts performance, but with our new transformer method, it keeps the detection rate at a low enough FPR that you might be able to use this in practice. And then, you know, we have lots of limitations with research and other future directions. And that's it. Thanks to our funders.